Hello friends, welcome back to this video. In this video we are going to discuss the binary random process. We have already discussed the random process, its mean, autocorrelation function and various numericals based upon the random process in my previous videos. I hope you all have gone through those videos and you don't have now any doubt in between the mean and autocorrelation function of the random process. If you still have any doubt, please watch my previous videos, then come to this video, because here I'll be using mean and autocorrelation function. So now here I am discussing the binary random process. So what is binary random process? The random process, as I said, it's a random variable which is a function of time. So now here I have binary random process, which means I have a random process. So random process will always be a function of time, and now its amplitude is having only two levels. So for example, if I have the polar line encoding, so in polar line encoding I represent 1 with the positive amplitude and 0 with the negative amplitude. So in the polar line encoding I have binary random process, because I don't know where I have 0, I don't know in the data where I have 1. So data is random. According to that I have generated a pulse which is random and it is having only two levels, so it is a binary random process. So let's understand this with the help of this example. I have taken a basic random pulse. So PT is my basic random pulse which is having the amplitude 1 and it is present in between the duration 0 to capital T. So this is my PT. I have done its NRZ encoding. Okay, so now here I have any data. The data is random. Here I have taken the data to be 0110. The data could be anything. It can be 0101 or all ones or all zeros. So data could be anything. The data is random now. And here I have done the polar NRZ line encoding, like the way I said. In the polar NRZ encoding we have generated the binary random process. So if I have to generate the binary random process, I'll be taking the polar NRZ representation of this data. Okay, so now here 0 is represented by the amplitude minus A and 1 is represented by the amplitude A. Here also 1 is represented by the amplitude A and 0 is represented by the amplitude minus A. So here we have specified duration. Each duration is capital T. Okay, so now here if I have to generate this signal with the help of basic random pulse, so how can I generate it? If I take this pulse and now if I multiply it with minus A, so I can generate this pulse from 0 to T. I'll be having the reverse of amplitude and the duration is same. So it is minus A into PT. Now if I see the next, so now the next is represented by A amplitude and now time is shifted. So time is in between T to 2T. So how I can represent it with the help of this pulse? I can shift this pulse by T. So how I can represent it? I can represent the amplitude A and P T minus T. Minus T represents the shift of T in the positive direction. So I have shifted this in the positive T. So here I have same amplitude and now it is shifted by 2T. So here A P T minus 2T. So again it is minus of amplitude. So I'll be multiplying with minus of A and again I'll be shifting with minus 3T. So here minus A P of T minus 3T. So now if I have to represent this random process, so here I hope now you don't have any doubt that how this is a random process, because the data was random and now this signal has only two levels. So it's a binary random process and it is dependent upon time as well. So it's a random process. So now here if I have to represent this random process, I used to represent the random process with T. So it is x of T. This is how I used to represent a random process. So here what I can do, I can take summation of all the PTs. So here what I have done, I have multiplied them with the amplitude and I have shifted them with the K. So I have taken summation all over K and k is varying from minus infinity to infinity, ak p t minus kt. And now the value of a are just two values. I have plus a and minus a. So a is a random variable here, which is a discrete random variable. So here you can see I have just two values, so I can say a to be discrete. Okay, so now a is discrete random variable having only two values, plus a and minus a. So now when a is changing, so xt can be represented as a random process, because xt is dependent upon time as well as a random variable. So xt is my random process. So now coming to the another variable on which my random process is dependent. So here if I have taken the delay time as well, here what I have taken that the pulse is originating from 0 time only, but let's suppose I have some delay time. So here let's suppose the pulse is originating at td. So here the pulse originated, so from here the pulse started. So this is td. Okay, this is my delay time. Now what is the delay time? Delay time is only present in between 0 to capital T. It can never be greater than capital T. So let's suppose here I have taken the case that TD is greater than capital T. So that time what will happen? So here I have, this is, okay, this is my TD. So this was my TD, but the delay time is only considered when the first pulse start. So now here it is greater than capital T as well. So this is capital T and this is the remaining time. So here the pulse has started. So now this remaining time is the new TD dash. So now here I have seen that the TD can never be greater than capital T. Whenever it is greater than capital T, that time a new pulse will be generated and it will again be lesser than capital T. So the TD is also a random variable which is present in between 0 to capital T. So now how I can represent this TD? TD is also a random variable. So TD is a continuous random variable. Here A was discrete random variable, but here TD is a continuous random variable which is uniformly distributed from 0 to capital T. So here I have represented it. If I draw the PDF, so f of TD represents the PDF of TD. So PDF of TD is represented by f of TD. So it's a uniform distribution between 0 to capital T. So amplitude would be, obviously it would be 1 upon capital T. So now if I have to represent the pulse again in the form of TD as well. So here I have initiated another random variable which is TD. So now my random process is composed of two random variables. First random variable was AK and now I have inserted TD as well. So here random process can be represented as summation n is equal to minus infinity to infinity AK P T minus KT minus TD. So here I have represented it with the TD delay as well. So now here AK is my discrete random variable. As I have already told you, it has just two values, minus A and A. Now TD is my continuous random variable, so it will be represented by 1 upon B minus A. What is B? It is T, and what is A? It is 0, so 1 upon T. So 1 upon T minus 0 would be 1 upon T only, so here it is represented by 1 upon T. Now AK and TD are independent upon each other. So now here these two don't depend upon each other, and I hope you remember what happens when two random variables are independent. We'll be using this property when we'll find out the autocorrelation function. So here we'll be finding out the autocorrelation function of this binary random process. I hope you remember how I can find out the autocorrelation function. to find out the autocorrelation function, I used to take the random process, I used to shift it by tau, and I used to take its mean. So here R of tau represents the autocorrelation function. It is equal to E of xt multiplied by x of t plus tau. So here I'll be just putting the value of xt and xt plus tau. So I hope now you understand what is xt plus tau. If in this equation I represent t with t plus tau, so it will be xt plus tau. So now what will be xt plus tau? So here I'll be representing xt plus tau as well. So xt plus tau is equal to summation n is equal to minus infinity to infinity ak p. So instead of t, here I'll be putting t plus tau. So rest of the things will be same, minus kt minus td. So this is my xt plus tau. So now I know what is xt. Now I know xt plus tau. I'll be putting in this equation. So I put the xt plus tau. I cannot take the same variable. So one variable I took as j and another as k. So instead of n, I have taken them, the variables, in the form of j and k. So now here I have taken R of tau, which means the autocorrelation function is equal to mean of, so here I have put in the value of xt and I have taken the variable j. So summation j is equal to minus infinity to infinity a of j p t minus jt minus td. So instead of k, I have put here j. So now here it is summation k is equal to minus infinity to infinity ak p t plus tau minus kt minus td. So here I have taken this x of t plus tau and I have multiplied it. So now what I have done, I have taken the summation together and I have taken aj and ak together and the pulses together. So now here aj and ak represents the amplitude. Amplitude and pulses are independent, as I already said. So now if two random variables are independent, so a into b can be represented as ea into eb. So now this is the condition of independence. So this condition I have used here. So e of ab is equal to e of a into e of b. Okay, so now here I have taken summation e of summation j is equal to minus infinity to infinity, summation k is equal to minus infinity to infinity aj ak p of t minus jt minus td p of t plus tau minus kt minus td. So now I hope up to this point all of the things are clear. Now I'll be taking j is equal to k plus n. So I am taking the j to be shifted version of k only by n. So j is shifted by k by n only. So here j varies from minus infinity to infinity. You can see j is varying from minus infinity to infinity. So now put the value of j here, minus infinity. So now when I put the value of j minus infinity, n would be minus infinity minus k. So n would be minus infinity, and when I put j is equal to infinity, n would be infinity. So now I concluded that when j is varying from minus infinity to infinity, my n is also varying from minus infinity to infinity. So now here I have represented the autocorrelation function in the terms of n. So now instead of j, I'll be putting k plus n. So n is changing from minus infinity to infinity. I have taken it on the summation. Now I have taken e to be inside. So e of ak plus n ak. So now this is e of ak plus n into ak. What is this? It is the autocorrelation function. So I can represent it as the autocorrelation function of the amplitude. So here it is the autocorrelation function of the amplitude. This is why I changed the j. So now here when I change the j, so here I have put in the j as it is. So now I'll be changing the j here as well. So E of P t minus jt minus td, P t minus kt minus td plus tau, I have represented it as it is. So here I have chosen this to be alpha and this to be beta to simplify my equation. So t minus jt minus td is alpha. So instead of j I will be putting k plus n. So t minus kt minus nt minus td is equal to alpha, and t minus kt minus td plus tau is beta. So I have chosen it to be beta. Now I am supposing that t minus kt minus td is equal to u. So now here I have to find out all of the parameters in the terms of delay time only, because I know the amplitude I have already simplified. Now I need to simplify in the terms of delay time as well. So when I consider the delay time, what will I do? I'll take in the terms of delay time. So differentiation in the terms of delay time would be minus dtd, so it is equal to du. So now here if I represent alpha in the terms of u, so what would be alpha? So this t minus kt minus td, so this is u, so now it is equal to u minus nt. Similarly if I represent beta also, so t minus kt minus td, this is u, so it can be represented as u plus tau. So now I can represent my p in the terms of u. So now here I have r of tau is equal to summation n is equal to minus infinity to infinity e of ak plus n into ak. I have already told you I can represent it in the terms of autocorrelation function of a. So now here I have summation n is equal to minus infinity to infinity, sorry this is k because n I have already taken, so it is e of p alpha into p beta. So I have represent this as alpha and this as beta. So what is e? I hope you remember. E can be found out using taking the integration from minus infinity to infinity. So it is p alpha into p beta into f of td. So f of td is the PDF in the terms of td delay time and dtd. So now here I know f of td. F of td is 1 upon t. So here I will be putting the value of f of td. So I will be taking it outside because it does not depend upon k or td. T is constant. I have taken t to be bit duration time. So bit duration is constant. I have taken it outside. So it is n is equal to minus infinity to infinity r a tau. So here k is equal to minus infinity to infinity. Here because my f of td is only in the interval 0 to t, so here I will be taking p alpha p of beta into dtd. So now I'll be converting it in the terms of u. So now in the terms of u it will be 1 upon t summation n is equal to minus infinity to infinity r a tau summation k is equal to minus infinity to infinity. So now when I put capital T is equal to 0, so capital T, sorry TD is equal to 0, so that time U is equal to, so here U was, I have to change the limits, no, so U is equal to T minus KT minus TD. So now when TD is 0, so here I will be changing the lower limit, so put TD is equal to 0, so here I have T minus KT as the lower limit. So again in this let's put TD is equal to capital T, so upper limit I will be putting TD is equal to capital T. So when I put TD is equal to capital T, here I have T minus K plus 1 T. So here T minus K plus 1 T. So now here I have alpha in the terms of u as well. So what was alpha in the terms of u? So it is u minus nt, and what was beta in the terms of u? It was u plus tau du. So this is minus du, because dTd is equal to minus du, dTd was equal to minus du. So now here if I have to remove this minus sign, what will I do? I'll change the limit. So it will be equal to 1 upon t summation n is equal to minus infinity to infinity r a tau summation k is equal to minus infinity to infinity. So upper limit will be coming downside, t minus k plus 1t, t minus kt, p u minus nt, p u plus tau du. So now here I am changing k from minus infinity to infinity. So here I will be having 1 upon t summation n is equal to minus infinity to infinity r a tau. So here if I change k from minus infinity to infinity, so this integration limits will change, and here I will be having minus infinity to infinity p u of minus nt p of u plus tau du. So now here what is this? This is also the autocorrelation function of the pulse. So what is the factor of the autocorrelation function? How I used to find out the factor of the autocorrelation function? Here the factor would be this minus this. So here t plus tau minus t is equal to tau. So it is the factor of the autocorrelation function, which is tau. So here if I need to find out the factor, so it would be u plus tau minus u plus nt. So now it would be tau plus nt. So this is also the autocorrelation function of the pulse. So it is 1 upon t summation n is equal to minus infinity to infinity autocorrelation function of amplitude in the terms of tau. Now it is multiplied by the autocorrelation function of the pulse in the terms of tau plus nt. So it's the shifted autocorrelation function of the pulse. So now I hope you understood how I can calculate the autocorrelation function of the binary random process. So here if I need to find out the power spectral density, I hope you remember, if I need to find out the power spectral density is the Fourier transform of the autocorrelation function. So what I'll do, I'll be taking the Fourier transform of this function. So now I have already found out the power spectral density of various line encoding technique, and the basis of all of the power spectral density was this only. So here with the help of this equation I can find out the power spectral density of any of the type of line encoding scheme, like unipolar NRZ, polar NRZ, alternate mark inversion, which is also called bipolar NRZ, Manchester. So I have already covered those in my digital communication part. I hope you all have seen that. If not, now you can see them. So you'll be understanding how I have computed the power spectral density. So here I'll be stopping my discussion. I hope you understood each and everything. If you still have any doubt, you can put the doubt in the comment and I'll try to resolve it as soon as possible. I hope you like this video. If you like it, share it with your friends, subscribe the channel and push the like button. Thank you.